Friends, last time we already discussed the examples of reaction of carbon-carbon double bond, and you know carbon-carbon double bond gives the electrophilic addition reactions, and we discussed the various examples and its mechanism. So today we are going to discuss the reactions of carbon-carbon triple bond. Similar to the carbon-carbon double bond, carbon-carbon triple bond gives the addition reaction or electrophilic addition reaction. Suppose we take one simple example and you discuss the addition of hydrogen. We know in case of the carbon-carbon double bond, the alkene reacts with a hydrogen and there is formation of alkane. So similarly, suppose we take a carbon-carbon triple bond and you take a various reagent. Suppose here you take a catalytic hydrogenation in presence of nickel or palladium. Then this carbon-carbon triple bond, the 2 moles of H2 they are added to the carbon-carbon triple bond and there is a formation of carbon-carbon single bond, means the formation of alkane. So that's why, so what happens in case of the carbon-carbon double bond, we reduce using the catalytic hydrogen, then 1 mole of hydrogen is required here because one carbon-carbon double bond is there. So that's why 1 mole of H2 is there and to form the alkene. But when you take an example of carbon-carbon triple bond, then 2 mole of H2 they are added to the carbon-carbon triple bond and there is formation of a alkane. Then you take a next example. Suppose you take this simple example and you take a H2 in palladium in barium carbonate. So such type of reagents we use, and these reagents we call the Lindlar catalyst. And when we use a Lindlar catalyst, then we get this type of cis compound. So this is a selectivity in case of this Lindlar catalyst. You take a carbon-carbon triple bond, they are treated with H2 in palladium in barium carbonate. These reagents we call the Lindlar catalyst. And when we use a Lindlar catalyst to reduce the carbon-carbon triple bond into double bond, then we get a cis type of compound. Again, you take a same starting compound and they are treated with sodium in ammonia or lithium in ammonia. Then what happens? We get a trans compound here. So this is some reactions of carbon-carbon triple bond. We want to carbon-carbon double bond. We reduce the carbon-carbon triple bond into the alkene and we want a cis compound. Then we use a Lindlar catalyst. Suppose we want a trans type of compound. Then we use there is a sodium in ammonia or lithium in ammonia. So this is some examples of carbon-carbon triple bond and that is called the addition of hydrogen. Suppose, so what is the mechanism of electrophilic addition? Mechanism of electrophilic addition to the carbon-carbon triple bond. Suppose let us consider the example of this is your carbon-carbon triple bond and this carbon-carbon triple bond is added by using the acidic reagent HX. So suppose this HX is added to the carbon-carbon triple bond, then what happens? We know this hydrogen having the delta positive, chlorine having the delta negative charge, and this carbon-carbon triple bond or double bond, the first electrophile is added to the carbon-carbon triple bond and this step is a slow step. And once this carbon-carbon triple bond is added, then what happens here? There is a formation of that is a phenolic cation. And how the phenolic cation formation takes place? We write this way. Then we form this is cation, and we write this type of intermediate. So we call the phenolic cation. And once the phenolic cation formation takes place, then your reaction mixture having that is X minus, and this X minus is attack on this carbocation. When X minus is attack on this phenolic cation or carbocation, then there is a formation of such type of compound, this one, and we get here the carbon-carbon double bond. So what happened in this case, the first molecule of HX is added to the carbon-carbon triple bond. The first step is slow step, then we get a phenylic cation, and once you get a phenylic cation, in second step what happened, X minus is attack on a carbocation, and there is a formation of here the phenyl halide. Then again the next molecule of HX is added to the phenyl halide, and when this HX is added to the phenyl halide, then the addition is again according to the Markovnikov addition, and we know then again there is a formation of a cation, this one. And when this cation formation takes place, again your reaction mixture having the X minus, and that's why this X minus or nucleophile is attack on this carbocation, and then we get this type of compound. So this is a simple example of the addition of HX to the carbon-carbon triple bond. And then what happened in this case, the first HX molecule is added to form the phenylic cation. To that carbocation, the X minus is attack to form the phenyl halide, and then the second molecule is simply attack on this carbon-carbon double bond, and then there is formation of a carbocation. Then nucleophile X minus is attack on this carbocation, then we get a final product. So in this way, this is simple mechanism of addition of HX to the carbon-carbon triple bond. Then you take a next example. Suppose the addition of or halogenation or addition of Br2. We take this is carbon-carbon triple bond. That is Br2 is added. The first one molecule of that is Br2 is added. Then we get this is a dibromo compound. This one. Again the second molecule of Br2 is added to the carbon-carbon double bond, and then we get this the tetra-bromo compound. So this is the addition of halogen to the carbon-carbon triple bond. So in case of the double bond, 1 mole of Br2 is added and to form the dibromo derivative. But when we take a carbon-carbon triple bond, then 1 mole of Br2 is added to form this type of dibromo derivative. Again the second molecule of Br2 is added and to form the tetra-bromo derivative. So that's why this is the second example. So we call the addition of that is Br2. Then what is the mechanism of this addition? The mechanism is similar to the addition of carbon-carbon double bond. Then here we take a next example, and then we take one addition reaction, the addition of water molecule called the hydration. And when you take a carbon-carbon triple bond, any example, you take this one, then water molecule is added in presence of concentrated H2SO4 and in presence of that is a HgSO4. Then what happen here? The addition reactions takes place, and to form here, this is a enol form. Once there is a formation of enol form, this enol form is converted into the keto form. And this is the keto. So we remember enol and keto, they are the tautomer to each other. So that's why when the addition of water molecules takes place in presence of H2SO4 in HgSO4, there is formation of enol, and this is a formation of the keto. So enol and keto forms, they are the tautomer to each other. So this is a simple addition reaction of water molecule. Then suppose a terminal alkyne. You take a terminal alkyne, and this terminal alkyne, they are treated with heavy metals like AgNO3. And what happen? This hydrogen is abstract by these heavy metals, and then there is a formation of a carbanion, and we get this type of metal acetylides. Because you know, this is a terminal alkyne, or this is hydrogen. This hydrogen is directly attached to this carbon-carbon triple bonded carbon. So that's why this hydrogen is acidic in nature. And when the heavy metals like that is silver or magnesium, they are treated with this type of terminal alkyne, then this hydrogen is abstract and there is formation of such type of acetylides. So means as like a carbanion. Suppose we take this example and we write attach this compound we treat in a methyl magnesium bromide, such type of compound. Then what happened here? There is a formation of this type of acetylides of magnesium. So this is a very important reaction and to form the higher alkyne. Because you take a terminal alkynes which having the 3 carbons, then they are treated with AgNO3, or that is heavy metals like magnesium. There is formation of acetylides, and these acetylides is act like a carbanion. So that's why this carbanion is useful for the preparation of higher alkynes. Then once we discuss this, then we discuss the reactions of carbon-carbon or carbon-oxygen double bond. Reaction of carbonyl group or carbonyl or carbon-oxygen double bond. When we see the carbonyl compound, and we know this carbonyl oxygen having the electronegative, so it having the delta negative charge, and this carbonyl carbon having the delta positive charge. We write a resonating structure of that. This oxygen having the electronegative than the carbon, so oxygen get the negative charge and this carbon get a positive charge. So what happened here, once you think about this carbonyl group, then this carbonyl carbon having the electrophilic character. And what happened? When you take any nucleophile and this nucleophile is added to the carbonyl group or carbonyl compound, then this nucleophile is attacked on a carbonyl carbon, because this carbonyl carbon having the positive character, or it act like a electrophile, and when we add a nucleophile, then the reactions are takes place. So normally this carbonyl carbon or carbonyl compounds gives the nucleophilic addition reaction, because this carbonyl carbon having the positive character and we add the nucleophile, then the reactions are takes place. So that's why the carbonyl compound mainly gives the nucleophilic addition reaction. Then what is the next part? The reactivity of carbonyl compounds. Reactivity carbonyl compounds. All the carbonyl compounds don't have the same reactivity towards the nucleophilic addition. Suppose we take one simple example. You take the aldehyde, you take this second aldehyde, like for acetaldehyde, you take a ketone, and then we think about what is the reactivity of these 3 compounds. So the first compound is more reactive than second. So second compound is more reactive than the third. So this third compound having the least reactivity towards the nucleophilic addition than the first compound having the more reactivity. So which factors there affects on the reactivity of carbonyl compounds? So there are the 3 factors which are affect on the reactivity of carbonyl. The first one is the inductive effect. And what happened in this case? Inductive effect means there are the 2 type of inductive effects. There is a plus I and there is a minus I. So what is the effect of electron donating groups and what is the effect of electron withdrawing group on the reactivity of carbonyl compound? So we take simple one example here, and you take one the acetone and second one you take acetyl chloride. So what is the difference between these 2 compounds? So the first compound having the less reactivity, second compound having the more reactive towards the nucleophilic addition. So reason is that when you take an acetone, there is a 2-methyl group and both the methyl group gives the plus I effect, electron donating inductive effect. What is the effect of this methyl group? So methyl group donate the electron to the carbonyl carbon, and then what happen? Ultimately, what is the positive character of that carbonyl carbon is decreases. Means positive character of carbonyl carbon is decreases is nothing but the electropositivity of that carbonyl carbon is decreased, or electropositivity is decreased. Then ultimately what happen? Electrophilic character is decreased, and when the electrophilic character is decreased, then ultimately this carbonyl having the less reactive towards a nucleophilic addition. But what happen here? This methyl group gives the plus I, electron donating inductive effect, but this is a chlorine gives the minus I effect, and that's why what happen here? When the chlorine pulls the electron from this carbonyl carbon, then the positive character of that carbonyl carbon is increased, and when the positive character of that carbonyl carbon is increased, means electrophilicity is increased, and when the electrophilicity of positive or carbonyl carbon is increased, then ultimately this carbonyl carbon or this compound having more reactivity towards a nucleophilic addition. So what is your conclusion? When there is electron donating groups which are attached to the carbonyl carbon and which give the plus I effect, then the reactivity is decreases because the positive character of carbonyl carbon is decreases. When the electron withdrawing groups they are attached, it pulls the electron from carbonyl carbon. So positive character of that carbonyl carbon is increased, means electrophilicity is more and more, and such case or in such cases this carbonyl carbon having the more reactivity towards a nucleophile, and that's why this carbonyl compound having the more reactivity. So this is the first effect, that is the inductive effect. When you take a next example, suppose you take various aldehydes, and here you take a nitro group, then you take a chlorine as a substituent, or suppose here you take a bromine as a substituent. So suppose we compare the reactivity of these three compounds. So nitro is a more powerful electron withdrawing group than the chlorine, and chlorine is more powerful than the bromine. So what is the trend of reactivity? Here the first compound is more reactive than the second compound, and then the third compound is the least reactive towards the nucleophilic addition reactions towards the carbonyl. So nitro is a more powerful electron withdrawing group, so it gives the more and more minus I effect. The chlorine having the less ability to withdraw the electron, and bromine having the least ability to withdraw the electron from this carbonyl carbon. So that's why this compound having the more reactivity, then second, and then the third one. Then the second factor is there, and which is second factor? This is a resonance effect. This is second factors which affect on the reactivity of carbonyl. That is a resonance. That's why we take one simple example, and you take this is aldehyde. At para position there is a nitro group. Then you take a simple benzaldehyde. There is no substituent at aromatic ring system. Then you take a para-methoxy benzaldehyde. This one, and again you take this is the two phenyl ring system which are attached to the carbonyl carbon. So what is the reactivity in this case? So means we remember what happened in this case. This is the nitro group, and in this case this nitro group is the pull the electrons, so it gives the minus I as well as minus R. And in such case, what happen? This nitro group pulls the electron from this ring system, and this ring system pulls the electron from this carbonyl carbon. So that's why what happen? This whole system is act as an electron withdrawal, or it withdraw the electron from carbonyl, and that's why this compound having the more reactivity towards a nucleophilic addition. Then what happened here? this is aromatic ring system, and this aromatic ring system, what happen? It gives them plus R. This ring system or aromatic ring system donate the electron to the carbonyl carbon. So what happen here? Here the nitro group, it's act as a minus I as well as a minus R, but this ring system gives the plus R. So ultimately the reactivity of that carbonyl carbon is decreased. So this is second one. Then when we compare second and third, so third having the less reactivity as compared to the second, because this is the methoxy group, and methoxy group donate the electron as like this, and then this methoxy is act or it gives the plus R. And when methoxy gives the plus R, then this methoxy group donate the electron to the ring system, and this ring system again donate the electron to the carbonyl carbon. So here this methoxy as well as this ring system donate the electron. So there is a plus R effect is more as compared to second, and that's why third compound having the less reactivity towards than the second. But when we take the example of last one, and here is a such two ring system is there. So this ring gives the plus R effect, this ring gives the plus R effect. So in last case the electron donating resonance effect is more and more due to this two ring system, and that's why what happen, this compound having the less reactivity as compared to all these three compounds. So the second important factor, that is the resonance effect, means when there is a electron withdrawing resonance effect is there, then the positive character of carbonyl carbon is increased, reactivity is increased. When there is a plus R effect is there, means electron donating resonance effect is there, the positive character of carbonyl carbon is decreased, and ultimately reactivity is decreased. So in this way, this is a reactivity sequence or increasing order of reactivity of this four compound, means the resonance effect is also important to decide the reactivity of carbonyl carbon. When there is a minus R, the reactivity is increased, and when there is a plus R, the reactivity is decreased as like a inductive effect.